Good morning. In this demo, we are going to observe and visualize the decay of fluorescence from a ruby crystal. For this, we will need three things. First is a photographic flash. Second is a slow motion capable digital camera. In this case, I am using ASI 662MC, which is astronomy camera, which is fairly low cost. Even a cell phone camera or any other digital camera can also be used. And last but not the least, a sample of ruby. In this case, I am using a sample of a ruby earring, which consists of synthetic ruby. Next, so how do we make a setup for this demo? I have prepared some 3D models which can be printed with the help of a 3D printer. The model essentially consists of 4 parts. One is the base on which everything will be mounted. This is a sample holder where the ruby sample will be mounted. This is a camera holder where our digital camera will be mounted, and this is the flash cold shoe where our excitation flash will be mounted. Along with these 3D printed parts, we will also need a number of quarter 20 nut and bolts. Now we will look at the assembly of the setup. First, you will notice that I have put a quarter 20 insert in these 3D printed parts so that they can be mounted on this base using these quarter 20 screws. And in order to insert these, you can take help of your teachers or somebody who is familiar with working with 3D printed parts. But it is fairly simple. Essentially, you need to heat the parts up, heat these metal insert up, and then put them into the 3D parts. Now, first thing is, this is the cold shoe where our flash will be mounted. So in order to mount this to the board, we will go to on this extreme end, put the screw from the bottom, and simply screw it in tightly. So next is we have to mount this part. This is where our sample will go. So we'll take another quarter 20 screw and again screw it from the bottom and make sure it is straight. So this is mounted. The next we will mount the camera holder. So again the same thing, we will essentially screw the parts in, make sure these parts are fairly tight, no need for them to be extremely tight. So all these are properly mounted. Now for stability, we can put another screw on this end, and then we can go on starting to put component on our assembly. So first thing, we are going to mount this flashlight, Sunpack 422D, which is fairly straightforward. We can simply insert this into our cold shoe. And you can tighten the screw from here, so it's fairly well mounted. Next, I'm going to mount the ruby sample. In this case, the sample is a ruby earring, as you can see here. Now in this sample holder, there are several small holes, so you can put at this sample at various different heights, and as you know, there is something to lock it, so I can very simply put this earring onto one of these holes, insert it all the way through, and then I can lock it from behind. So now our sample is mounted. Now we are going to see how to mount the camera. Mounting the camera is fairly straightforward. So there is a space in this mounting holder and there is a quarter 20 socket. So you can simply mount the camera like this and you can adjust the height of this camera essentially to make sure that our sample is in the center of the field of view. Now our setup is ready. The camera is connected to the laptop through this USB 3 cable. Our sample is properly seated on the sample holder and our flash is ready. I will turn on the flash and then I will open SharpCap in computer. I will select the camera. To begin with, you can select zoom here as 50%, go to camera control, capture area, go to the largest capture area, make sure that the color space is row 16 and output format is fits files. I like to keep exposure quite short, it's 0.2 millisecond, and then I will increase gain here to 600 to see my sample. I can see that my sample is fairly centered, so I can go ahead and then select a custom capture area which I will put 200 pixel width and 100 pixel height. So now the capture area is very near to where my sample is. I will zoom the display to 300% and from this pan and tilt I can center my sample. And if the sample is not in the focus, you can essentially focus it by moving this, turning this lens ring in front of the camera. But the focus seems quite alright at this point. And I'm happy with this focus. I can see down here that the frame rate is 540 frames per second roughly. So I can go here, reduce gain back to 1, and then I can check here that it is selected unlimited. Then I just press quick capture and then press the orange button to excite the sample, and then I press stop capture. Some of the frames are in the buffered memory which are being written. And as you can see here that it has captured 3267 frames at a rate of 516 frames per second. Now we can go to this location and we can see that all the frames are written. Now we need to find which of these frames contains our data, and then we have to analyze the data. So the first step in data analysis that I do is I rename all of these frames, because that way it's easier for a simple program to work with these files. I'll simply delete the setup file and I select all of these frames and put them onto a free software. It's called Advanced Renamer, and you can use all the settings that are here. All the files are here, and I just click Start Batch, Start, and very quickly you can see that all the files are renamed. After renaming these recorded frames, next step is to find the frames which have the relevant data. So in order to do that, I will use a few lines of code. and you can go here, plugin, new macro, and you can paste these lines of codes. So this is n is essentially the number of frames, which in my case here is 3267, and this is essentially the path where the data is located. And what this code will essentially do is open all of these frames and take an average intensity reading and just write it in a output, and then we can see which frames contains relevant data. So I'll let it run because there are several thousand frames, so it may take a couple of minutes or 3-4 minutes. So now it has finished looking at all of these images and recorded their mean intensity. So we'll save this result as somewhere, maybe I can see here. I will just save these results here, and then I can open this file. So this first column is frame number, and this is the mean intensity. I can simply add a chart here, and in this chart I can see that the frame where there is a lot of intensity is there, so it's near 1473. So I know that the frame where the light came initially, where the flash pulse came, was at 1473. If we want, we can look at it in a little bit more detail. So we can see, if we can already see an exponential decay here, but we will come to that later. First we will just look at these frames where this data is and try to visualize how the fluorescence is decaying. So what I can do is I can go back to my images, and I can copy the frames starting from maybe like 1467 to maybe 1500. After identifying the frames which contains the pulse and the relevant decay data, now I take all of these frames and put it in the software called PIPP. PIPP stands for Planetary Image Preprocessing. It's a free software. So you want to drag all the images onto this software here, and then make sure you arrange them by their file name. Then in the input option, make sure that you select debayer raw image file, and input frame select as monochrome, and then select debayer monochrome frames. This camera have this pattern GBRG, so that will correctly debayer. And after that, in the output, you select output as AVI, uncompressed raw, and here if this box is checked, uncheck this and select frame rate as 5 frames per second, and then just start processing. What it will do is it will take all these frames and make a video out of these frames, and the video will play at the rate of 5 frames per second. So this is the video here. We can either play it in a VLC player or in image J. So in the VLC player, when I play it, you can see that as the flash pulse came, the ruby kind of glowed quite bright and then decayed in its brightness. I like to open this with image J, which essentially makes it very easy to move between the frames. So I zoom it a little bit, and then just I go here with these scrollers. So this is where the flash came. You can see some white light, some of the flash is clipped, and then you can see the ruby started to glow really bright, and as the time passed, right, the brightness became lower and lower as the population from the metastable 2E state decreased as a function of time. So this is really interesting. I like browsing through these frames, and in the next step we will see how we can utilize now the intensity value from these frames to compute decay time and the rate constant of these electronic transitions. In our final step, we are going to take this frame data and we are going to compute the decay time parameters. That's the decay rate constant and the lifetime. So in order to do that, I will make one change than the analysis we did earlier, and that change is that I'm going to select a region of interest which only encloses the ruby crystal. In order to do so, first what I will do is I will enable a record macro. So that will make it easy to select a region of interest. And then I will select one of the files where ruby crystal is visible. Now if you look here, you'll see this checkerboard kind of pattern. So this is because of the Bayer matrix. There are red, green and blue filters right on top of sensor, and because of this the matrix appears. Now the simplest way to get rid of this is I can bin the image 2 by 2 pixels. So after that you can see that this Bayer matrix is eliminated, and now I can make a region of interest which only encloses this ruby crystal. So this is my region of interest, and in my recorder this region of interest has appeared, and I can simply copy paste this region of interest here. Okay. I can close this image now, and I will make use of this code. Here the N1 and N2 are the start and end frame number, in our case which is 1467 and 1500. Then it will go and first compute the time of the frame. So this chunk of the code essentially takes the timestamp from the frame and extract it so that we know that what is the exact time corresponding to that frame. After that it will bin this image and select our region of interest and do the intensity measurements there. So we will run this. So on the left side you can see these are the timestamps of our frames. If we look into the details, so this is the date followed by a T. So this is the time. The first is in hours, 20, 29, 30. So hours, minutes, seconds. And after that these are the fraction of seconds. So 0.412, so it's like 412 millisecond. And because we know our frame rate was about 500 frames per second, we can also see that roughly these frames are separated by 2 milliseconds each. So what we will do is we will save this file as So we will open this column we will simply delete, and we will copy Control A, Control C, all of these data points. Now this, the way imaging makes this data, we need to properly arrange this data into columns. So we go to text to column, and we can select all of these delimiting factors here. Rid of these. So again, now all the time is separated, but I only need the milliseconds, the last part of this. So what I will do is I will only extract the data after the point. So I will delimit it based on the decimal, and I can simply delete this. So now this is time, and in order to convert it into milliseconds, I can simply divide it by 10,000. So now I have obtained essentially the intensity as a function of time. First, we can simply plot it here before going to exact decay time analysis. I can give x-axis as time in milliseconds and y-axis as intensity. So we have a really nice looking plot already here, where we have essentially the mean intensity as a function of time. As the flashlight comes, the intensity increases and then it decreases exponentially. Now you will notice one thing, that when the flashlight is not there, this value is not 0, but it is some definite number. This is known as offset. So we need to be mindful of that. Either we can reduce offset here, or we can make an exponential fit along with the offset. So for this first point, when the ruby starts to brighten up, so this first point typically have the influence of the flash intensity. So for our fitting, we can eliminate the first point, and we can copy the rest of the data, and again go back to image J. We will go to Analyze, Tools, and Curve Fitting, and we go to Exponential with Offset because our data has offset, and we simply paste our data here, and then we ask to make a fit. So this fit looks really good. The R square value is 0.9999, and the offset that this has calculated is 1108, which is really very close to the 11112, the offset that we have in the data. So it seems like a really nice fit. And so the decay time constant, or the decay parameters, can be computed from this B value here. So B value here is essentially 0.21551, which is in millisecond. So essentially it's can be used to compute our decay lifetime. By taking a inverse of this B value, we can calculate the lifetime of our process. So this comes out to be about 4.64 millisecond, which is very close to the to the standard value of about 4.2 or 4.3 milliseconds. And in our case, the value is a little bit higher. Part of the reason is that the crystal is a little bit bigger. It's about 6 to 7 millimeter in diameter. And in a bigger crystal, what happens is that some of the emitted fluorescence is reabsorbed by the crystal and then re-emitted. Effectively, that results in an increase in apparent lifetime. So it's not surprising that the lifetime calculated here is slightly higher, about 4.6 milliseconds. At the same time, this B value also gives us a rate constant. So in this case, the rate constant is 0.21551 millisecond inverse, or we can also say it as 215.51 second inverse.